Yeah, he has been a speaker at MOG in the previous years. So he's a distinguished engineer at NVIDIA in the data center software organization, focused on GPU communications, both nickel and NVSMAM. He has extensive experience with the design and use of parallel programming models and scientific applications. Jeff's most notable achievements include the MPI 5 application binary interface standard. He presented on this in one of the earlier MOOCs, and for everybody's information, now MPI also supports the ABI. This is a big effort Jeff has led to have this interface between OpenMPI community and MPI, all the derivatives. So you can actually compile your application with one of these. Let's say OpenMPI can run with MPI or the other way around. So he has taken a big effort there. He has contributed, and also his contributions to the NWChem quantum chemistry project. So I was exposed to Jeff from his old days of NWChem projects. Many of you in the room also must have been exposed while he was at Argonne and all. So with that short introduction, Jeff, we'll move and try to listen to you. As I was telling, he has been working on this. Can you actually use agentic computing to write the MPI library itself? Okay, he's making jobs for many of us to be extinct very soon. Okay, so let's try
twice the price. Yeah.
So we have been doing MPI or MPH or MPI for AI, and he comes with a new approach saying AI for MPI, and all of us will retire. Okay, so with this, Jeff, please share your slides and get started. Yeah.
Apparently, I have to reboot WebEx.
Okay.
To share. So give me like 10
Sure.
seconds. I'm really sorry.
Sure. You can write an agentic stack now to reboot. Okay, I think we're coming. Okay, I think it is there.
Okay, good. So, and you can see
yes.
this. Okay, perfect. All right. Well, hey, the good news is none of us are out of jobs, as I'll show in a bit. Actually, the thing I think is what I've learned from this is that this actually makes my job way more exciting. And so I'll tell you about it. So as folks know, I've done MPI for a long time. I've done some other things. And so, you know, obviously NVIDIA has a strong interest in all the AI things, and agentic development is something that management has said, hey, this is cool, you guys should try this. So, you know, naturally, if I'm going to evaluate this tool, right, you can imagine I have a number of ways that I could be evaluating agentic development. Obviously, this is a joke because, you know, there's only one serious way for me as a quantum chemistry and MPI person to evaluate agentic development, because I should be evaluating things that I actually know what the right answer looks like. You know, if I do an iPhone app, it's going to be terrible because I wouldn't even know where to start. It would be insecure. It would crash. Who knows? So, you know, I don't know the Linux kernel, etc. So I focused on things where I could very clearly say, I know what success looks like, and I can help AI because, you know, the whole vibe coding thing, you know, it works until it doesn't. And then you have to actually use your brain to help AI. I find the agentic development process to be very, very similar to the wonderful experiences I've had over the years with many interns. You know, some of whom were incredibly talented, and you just iterate with them, and then some of them would get stuck, and you had to sort of sit down and say, okay, here, I'm gonna get you through this step, and I have to do that. So the tools, you know, you can imagine NVIDIA has a lot of these tools that they make available. So I use primarily Claude and OpenAI Codex. I use them both mostly interchangeably. Claude is maybe 5% better, but more expensive some of the time. And generally the practices are the same. The only real interesting difference I found is that the terminal interaction of Claude is worse, and Codex likes to write short get commit messages until you tell it not to. And I use some other tools, but they're not part of this talk. And the other thing, if you are doing agentic development and you're not in YOLO mode or dangerously skip permissions, you will spend all of your time hitting the yes key. And so don't do that. It kills your productivity. Get a Docker container with all your stuff in it, sandbox it off from, files you can't lose, and then let it just go crazy. And I did that for the MPI project, and I would say things like, hey, work on message rate, I'm going to bed. And in the morning, I would find the message rate would go up because it would do everything for 8 hours. So I named this project Vibe MPI when I started, and then I didn't vibe code it. So it's called Vibe MPI because I'm too lazy to think of a different name, and because it's sort of provocative, but it isn't vibe coded. I did a bunch of real work, and it's cool, but it isn't perfect either, and I'll show you why. So I'm in the Nickel team. I'm interested in fundamentally, can we use agents to develop communication software for Nickel and NVSHMEM, et cetera? Either our team internally or our customers externally. But the best way to evaluate this question is with the gold standard of communication software, which is MPI. It has all the things that we would like for this experiment. It has an actual specification. It has multiple high quality implementations for which the source code is available. It has multiple vendor optimized implementations that serve as a performance oracle on various platforms. And it has lots of tests. And I will say this, the specification is not adequate to write an MPI library. I think it is for humans because we kind of know and we've all hung out in the same room and we know what we mean, but it's not a machine readable spec. It shouldn't be. It's a great spec, but let's just not confuse ourselves. We need more than the specification to build MPI with an agent. And the tests are good, but they're not sufficient. And I'll talk about testing a bit later. Agentic development is very much a variant, in my view, of test-driven development. If you do not have tests, you do not have anything. You have to test your way through, and everything that isn't tested, it's frankly wrong. And I found some hilarious bugs in Vibe MPI that were caused by things not being tested, things that you'd never have to tell an OSU grad student or an Argonne staff scientist, hey, don't do that, because they're obvious. But AI was like, oh, I'm just going to use 8 gigabytes of eager buffers because it improves performance. And then you have to go in and be like, no, you actually can't use 8 gigabytes for buffering because users will be mad if you do that. And other interesting examples. So the method I used, I did not save all my prompts because I genuinely went into this thinking I would fail, and therefore I wasn't going to spend all this time writing down everything that I did if I was going to fail. So maybe I was a bad scientist, but I have the Git history for all my projects that may or may not help. But what I started out doing is I basically tried to build a database of MPI knowledge. So I downloaded all the user lists, got temporarily banned by my ISP. I downloaded all the papers, cloned the implementations, and that's important. I did not, Chinese wall this, as they say. I allowed agents to see MPitch and OpenMPI source code, and in theory they could have, cheated, but they didn't copy and paste code because I did everything in modern C++, and so there's some key differences. But they absolutely were capable of reading the source code and reading the comments and seeing the design. So I'm okay with that. Maybe it's a less clean experiment. But we all know that that's how we learn when we work together in the MPI community. We have permissive licenses, and you can sometimes the best way to learn a technique is to actually read code because we don't publish everything. And then the other fun thing, of course, because I put all these random sources of input into the databases, I then put in some bias. So I put in obviously some people we know who are experts in MPI, and I bias towards papers from DK's group and anything Bill writes, etc. And said prioritize those so that it wouldn't get. Sometimes AI gets really focused on some comment, and if some user says something that's wrong on a user list, I didn't want AI to prioritize that information, which might be useless. I started out by seeing if I could write a book about MPI. And I did. I have this mediocre book about MPI that I could make into a not mediocre book at some point, but it's not my priority. But of course, I think you can write books about things that you sort of understand, right? There's that that thing about those who can't do teach, which is a lie, and not nice to teachers. But it certainly writing a book about MPI doesn't mean you actually understand something. So I said, well, this is silly. Instead of writing a book, why don't I just try to actually build an MPI library? And as Feynman says, if you can't build the thing, do you really understand it? So this is a test both for me and for AI. And obviously, I've always dreamed of writing my own MPI library, but I think folks in the room will understand it's hard, and one person doesn't do it in any short period of time. A large group of people take many years to build a real MPI library, but AI was able to sort of, give me the cheat code to pound out 100,000 lines of code for an MPI library with my design. So I did, like I said, it's not vibe coded. I sat down and I channeled all those coffee hour conversations with Dave Goodell and Pavan and Rob and all the guys and then the MPI forum folks that I've interacted with over the years. And then I did design experiments, and I know that these design experiments have been done before, but I did them myself and I did prototypes. So when it came to the hardest thing in MPI to implement, which is message queues, receive with wildcards is by far the hardest thing that any MPI implementation does. Contrary to popular belief, it's not the 1,000 pages of functions; it's wildcards. And I did all the experiments, and I said, okay, is it? I thought, okay, maybe this algorithm is a good idea. Try this, and I just had AI spin up the code, write the experiment, write the micro benchmark, and then tell me which one is empirically the best on this system. And then I made a lot of progress with that. I have no intention of competing with anybody who's serious. So I didn't care about compiler portability or backwards compatibility with anything. I use C++20, all the STL functions. Some of that was maybe a little bit optimistic because using std vector for MPI eager buffers isn't the best idea in the world. But anyways, I used a modern C++ design, and it probably saved me a bunch of trouble re-implementing things in C that don't need to be re-implemented. I obviously, folks know I've written a few of the pages of the MPI standard, and I wanted to make sure I had all the features, even the unpopular ones like thread multiple and RMA. And so that was all in, and it was an ABI compliant implementation from day one because the stubs header is my MPI.h. This is an important point I want to share with folks. And I'll say this, I hate CMake personally. I won't use it if I have to write it, but the Agentic configure, compile, test loop is on the critical path when you do this AI-driven development, because AI writes code 1,000 times faster than any person. And so you write the code and then you have to compile the code and test it. And that's the loop. And CMake plus Ninja is incredibly fast compared to AutoTools and GNU Mika. I mean, when I configure MPitch, it takes like 2 minutes. And when I do CMake on Vibe MPI, it takes like 5 seconds. And that's a huge time saver. And of course, AI turns out AI is pretty good at writing CMake. It debugs CMake without me having to think. So I don't care. I will use any tool that AI can do flawlessly without me getting involved. Initially, I was just going to do the boring SHMEM and TCP conduits. I did OFI and UCX later, basically because I was like, well, I'm done with TCP and I don't feel like stopping, so let's see what happens. I had to do a full redesign for hardware tag matching support in those APIs. I am confident that my experience with that was pretty similar to the experience that MPitch went through with CH4, which they, of course, co-designed with some of the vendors over, I think, a year or two in the Coral 1 time frame. I did that whole redesign process in 2 days because I had a pretty good idea of what it would look like in my head, and then 2, I just had AI crank it out and write all the code, and if it didn't work, then I just said keep going and try again and throw stuff out and start over. And we got through that to use those APIs in less than a week. So this is the history of the project. I don't remember the first few prompts because they were part of another repo, but on May 26th, I had something resembling an outline of the front end of an MPI implementation, and I committed as Claude did stuff. I was then super excited, and I worked grad student hours, so I worked 7 days a week. Obviously, I didn't work 16 hours a day, but I did. The first thing I did in the morning and the last thing I did before I went to bed was I checked the agent and I said, what have you done? And then here's some stuff to do overnight. So I worked a lot of hours, and I emphasize that when people ask me how much it costs, because I did hit my $10,000 a month budget on the 28th of the month, working 28 days straight. And so what I can tell you is you probably won't spend more than 10K a month unless you're doing, multi-agent weird stuff. Because, and obviously 10K is a lot of money for some people, but in industry, that's not a lot of money. So I just want to, people ask me all the time, how much did I spend? I think Vibe MPI probably cost about $25,000 in tokens, which is about 1,000 times cheaper than the other MPIs that are out there by some DOE math estimate. I did. So I started on May 26th. By June 15th, I had single node TCP and SHMEM working. That means I passed all the MPitch tests that are passable by a generic implementation, and then plenty of other tests. It wasn't perfect, but it was really quite solid as an MPI implementation at that point. I did the OFI and the UCX, like I said, in a couple of days, and then I went on vacation. And when I came back from vacation, I got access to an IB system. Some of you probably know Gilad has the HPC Advisory Council cluster, which has some IB nodes in it. So I used that as my IB test system. And of course, I found a whole bunch of bugs because I'd done sort of virtual node mode with TCP, but I hadn't really done any serious multi-node before. And so obviously I cranked out multi-node support with all 3 conduits it took a little over a week. I worked on the launcher and then obviously all the IB wire up stuff that everybody knows. I then got invited to talk about it to HPE, and I did a slingshot port in 2 days, and that was a real mess. It was very difficult, and I'll talk about why that happened in a second. I will also say, this bump here, I split the tests out after a while because I realized I've written a few hundred tests, and they're really interesting tests that have never existed before, and I had to do them to actually get Vibe MPI to be correct. And maybe those tests are trivial for everybody else to pass because they had humans design them correctly from the start. But I'm going to release the test suite as a separate entity for the community because what I can tell you is I have access to every test suite, including some private ones that exist, and they were not sufficient to get me a working MPI implementation. So I had to write hundreds of tests based upon my knowledge of the standard and things that I could inspect and decide were broken, and from coverage analysis. So I have a lot of cool tests. So the code it's about 100,000 lines in total. 60,000 lines of it is the C++ implementation. 20,000 lines of it is tests, and then there's sort of 20,000 lines of extra stuff. Much of it like scripting related to agents, agentic wrappers around test harnesses, etc. And I have a big CMake system that pulls in every single external test suite that exists in the world. So I have at this point full MPI 5 support. I have pretty high confidence in the core stuff, data types, collectives, etc., well tested. Dynamic process management and sessions are a little brittle, but we can say that about other implementations as well. I have dynamic runtime selection of all the transports. I'm proud of that because not everybody has runtime selection between OFI and UCX, which I wanted to have because I don't like compiling MPitch twice on every machine I use. I did a bunch of stuff with matching algorithms. I have a no wildcard optimization that I don't think, at least nobody in the MPI forum told me that they had done before. That's a really important one, you know, because wildcards can be really expensive in some contexts. So it's a fun one to do. And of course, if you have AI writing code, it's not so hard to do it. I have RMA with active messages and with native. I assume COM threads because I love asynchronous progress, which is a design decision that's different from anybody else. I've implemented all the collectives, all the collective algorithms, including weird stuff. Like George Biros has this neat all V that nobody will implement in production because it's sort of either really good or really bad. And you know, MPI libraries don't have a good tool to select for it, and I just enable it as an option. So you could ask for it, and if you know that you're doing what George's team was doing with it, then you just flip it on the communicator, and it's great. And then I did Sylvain's algorithm for all gather that is only in nickel. So now I have that in an MPI library. I'm really excited about this one. I know it's maybe nobody else cares, but I really like to make MPI change at runtime. So I want to do every design experiment with one build. So I have every single tunable parameter hooked into environment variables and MPI-T and MPI info on comms or Windows. So I can basically redo any design experiment I had during the course of this project just by flipping some envars. And that's really useful for testing because I build once and then I can test every single path through the code by flipping the protocols on with the environment variables. So the test suites I use, obviously, MPitch, OSU, Intel. The IBM test suite for OpenMPI is private, but it's really quite, it includes some really weird tests that are hard to pass that I found quite useful. I use, obviously, a bunch of stuff I wrote and DOE wrote. I added hundreds of tests, and my total test bucket when I run Vibe MPI testing is about 2,000 tests, and I'm passing all the ones that I am capable of passing. There's a couple weird MPitch tests that are not required by MPI standard, but MPitch enforces them, and I fail them unless I flip on the MPitch compatibility argument. The thing that I did with AI that I think everybody should do, I ran the GNU code coverage analysis in the AI harness, and I drove test coverage to 99% in most places. So I went through and I ran the test suite, and then I said, show me the code coverage. And it was like 71% in data types. And I said, all right, you are going to write data type tests until we cover every single branch in that code. Maybe no user cares, which is why there's no tests. But if the MPI standard says it and it's in an implementation, that code needs to be tested. So I have generated the tests that allow me to get code coverage, at least in my implementation, essentially every line of code. ARMCMPI, which, you know, I've been using, it's part of NWChem at this point. You know, I've been using to break everyone's RMA library. But even that wasn't sufficient, so I added a bunch of RMA tests that are absolutely nuts, that I haven't yet subjected anyone else to, but we'll see what happens. And like I said, I'll ship this as a separate project, and I hope the community can benefit from it. This is the IB cluster performance. I can't remember which IB it is, but it's the one I think that hits 12 gigabytes a second. So I think people in the audience will know better than I will which IB variant that is. So there are 4 things on here. HBCX with UCX is blue, then that is my performance reference. Obviously, my colleagues work very hard to do a good job with that. The red one is my implementation over UCX, which is the only one which will be competitive with HBCX. The TCP and OFI are on there just to show that they work, but they're obviously transport limited in some cases. So you can see in the send receive plot, I'm doing pretty well. So on latency, I lose by a very, very small amount for very small messages. For RMA, my latency stinks compared to HBCX. This is because I like COM threads, and the asynchronous progress design I used, I think, has some latency overheads that don't exist in the native HBCX transport. And my accumulate, sadly, is not as good as I would like, and I haven't bothered to fix it because I didn't really know how it was until I looked at this plot. It does okay for global arrays tests, but clearly it's not optimal. So I could fix it, but I already have HBCX, and I'm happy with that for NWChem. This is message rate and sort of aggregate throughput, and I want to highlight the interesting divot in the red line here. This is a perfect example of AI does what you tell it to. So I told AI to optimize for latency, and I got a pretty good latency, as we saw in the other figure. I told AI to optimize for bandwidth, and so my asymptotic bandwidth is the same as HBCX. And I told it to do message rate, but at no point did I ever tell it that messages between 100 and 200 kilobytes, or whatever this is, I never told it to focus on those. And so apparently it's got some protocol issues in here that tank the bandwidth to less than 50% of peak. And I just need to go back and tell AI that, hey, you need to optimize this objective function for all the message sizes, and I'm sure it'll go put in a half rendezvous, whatever, some new protocol to fix that. The RMA is pretty much the same number you see on the previous thing, just shown a different way, which is HBCX is better. The small message latency is okay. The bandwidth is fine. In the middle, I'm losing, and my accumulate is disappointing. But as I am one of the only people in the world who really cares about RMA, I'm failing myself, but the rest of the world is pretty happy with these numbers. So I ran Lulesh because I talked to Livermore about this on Monday, so I wanted a number for them. I am competitive with HBCX on Lulesh. I think I beat them a little bit some of the time, but this is obviously Tinkertoy scale, 4 nodes and 16 nodes, not the showcase HBC scale. So it doesn't surprise me that I won at small scale, since that's where I did almost all my testing and development. But I beat them, I think, because my all reduce is a little bit faster in shared memory or something like that. But at least you could see from this would be a usable MPI in production for Lulesh, and it's good for other mini apps that I've tested. So the lessons I have, and somebody pop in chat if I'm going to get too close on time, but I think I have about 5 minutes. I did try the CXI provider for OFI and on a Cray machine, and it did not go well. And the reason is, and folks may know this, OFI providers are different. If you have the IB or the TCP or the CXI provider, they behave very, very differently, and you cannot treat OFI as a monolithic API. I pretty much knew that, but I didn't care, and I let AI see what it could do. And it turns out it did a terrible job. It took it 2 days before it really figured out how OFI worked. And even then, we still have some serious problems in my Slingshot implementation. What I figured out from this is that I needed to do a ground up analysis of the CXI provider, which I did with a separate agent. I told it to start from scratch, read the man pages, and write OFI native tests and do design experiments on how you would do an MPI prototype in the CXI provider. And from that, I then built a knowledge base, which I fed back into my Vibe MPI agent, at which point I finally got Vibe MPI to actually work for basic features. But the performance is trash and it hangs at scale because the CXI provider is very unforgiving of some protocol resource management things that the IB provider doesn't care about. And some of that you could say is hardware, some of it's software, and some of it's just me being dumb. Lastly, I want to say, just to be clear, like Vibe MPI is a research project. I intend to open source it and then publish it and then retire it. This is not going to be a product. This is not going to be something that I maintain. My hope is to have proved what we can do with agents and that other people will be wildly successful in doing their own MPI development in products, and that Vibe MPI does not need to exist in its own right, although it'll be there, and if somebody wants to take over, by all means, but it's not going to be something that I'm working on 2 years from now. Lastly, from the MPI perspective, you could build MPI from scratch using AI, but you can also make MPI libraries way better. So ARM-CMPI is a project that I care about, and I wanted to do a big update for request-based RMA, and I needed to QA it. So I threw the agents at it on the IB cluster, and I hadn't tested on IB in a while. And I found in very short order 9 different MPI bugs in both the foundational MPI libraries, and for both OFI and UCX. So essentially, I broke everything. Obviously, these are really subtle bugs that show up with ARM-CMPI usage, with request-based RMA, that have apparently not been tested very well over the years. And so I did a couple things. I ran the tests in the harness of the agent. I debugged them, meaning AI drove the GDB core backtrace analysis. I generated the bug reports that you can see linked on this page in Markdown, which I then reported after removing some stupid AI slop commentary. And then finally, so for MPitch, Huizhou is great, and I don't like to run MPitch's Clang Tidy, so I let them fix the bugs, but we did it all in a couple days because I gave them line numbers. But Tommy, who's our OpenMPI guy, he was on vacation, and I was like, well, I can either wait for Tommy to come back from vacation and annoy him with all my bugs, or I could just see what AI could do. So I told AI, hey, clone OpenMPI and fix all the bugs. And I just said, literally, go to GitHub and find all my bugs and fix them. And it did. It actually ran, obviously, one of these is just don't use OpenMPI 4, but the other 5, AI found, reported, and then fixed the bug, most of which were really subtle, small things, but hard to find without, by brute force, by human effort. And then I've submitted them, and I think George has merged 2 or 3 of these already. So within 1 week, I increased the quality of MPI RMA implementations a significant amount, entirely driven by agentic testing. So I really think this is even if you don't trust AI to write the code, you should trust AI to debug and break and debug your code, because those are easily or trivially verifiable tasks where if AI tells you have a bug, it's real easy to determine whether AI is correct. And the fact is, an MPI crash is an MPI crash. You don't need to question whether it's hallucinated. So what does this mean? I want to be very clear to all the funding people, all the people in management out there in the world. This is only possible because we have 2 high-quality open source implementations of MPI. And if those go away, 5 MPI isn't practical. You need an oracle and you need the intellectual foundation for AI to do this, because this is hard. Neither the spec nor all the tests in existence were sufficient. So I had to build, as I said, hundreds of tests to actually make this possible. And I did that because I know the MPI standard pretty well. And, you know, folks, I think OSU has experienced this already, but, you know, OFI is not monolithic, and you have to really focus hard on what your network is when you do OFI development. I will say, getting to full MPI 5 support is really easy with AI, and a lot of the features in the standard that not everybody supports can be developed with AI. And obviously, the MPitch family, including MPitch, tend to be feature complete. But you know, if you're an MPI library for a vendor or OpenMPI and you don't have all the features already, you can really up your feature coverage for many of these things with AI. Doing QA with it is awesome, and I will say, you know, I'm pretty good at MPI, and AI made me really productive. AI would not have given me expertise in something that I didn't understand. And to go back to DK's comment at the very beginning, AI is a power tool to make people who are MPI experts insanely productive and enjoy their development time better by not having to do git rebase and other nonsense. But it will not make you competent if you're not competent already. Can somebody give me a time check? I need to know how much time I have left.
Yeah, go ahead. Go ahead. We are
Okay.
running a little bit late, but we can catch up. Yeah.
Okay. All right. So this is real quick on nickel. So obviously this is my day job, but this is a topic, right? A lot of people have learned how to write MPI over the years, and nickel, particularly the device API, may be daunting to people who want to do AI research in comms. So I will say I've done a lot of research in nickel, and the method I use is very simple. I tell AI to download all the docs, all the source code, all the tests, and just read everything. And then once I have one successful project, I tell the AI to read the first project when it does the second, and this helps. AI has some fun things that maybe are kind of human-like. When I tell it to write comms code, it always does a great job with latency. The bandwidth over NVLink is trash. And then we discover that, in fact, AI only wants to use one SM to drive the network. If you know anything, NVLink is a 450 gigabyte per second link, and you cannot drive that bandwidth out of one GPU core, i.e. SM. And so you need to do lots of parallelism in your load store to drive that bus. And so AI and I have, of course, rediscovered this fact multiple times, and it'll be something that I would add to a skill for, you know, NVIDIA CommStack development, is remember how to develop parallel memory operations. I was really happy because I'm not a CUDA ninja. I was able to get AI to attach the Nsight compute profiler and do register, kernel, occupancy, all the fun optimizations that are, you know, people know how to do them, but they're hard, and the loop around the profiler can be tedious itself. And so AI fired up the compute profiler and said, oh, well, we got too many registers here, not enough warps here, etc. And I got, you know, order of magnitude improvement in my communication kernels that run on the GPU. And I've been able to do now both NVLink and the GPU-initiated networking development, that is complicated stuff. And I will say, unfortunately, the docs are not rich yet, and so there are not very many examples. But AI was able to figure it out from our, you know, relatively limited documentation, how to do rail-based GIN programming on a NVL72. Which this may be relevant because I think Dan has one of these, and I've been able to do some really cool comm stuff using an agent, and I did not know how to write this stuff before I started doing it with an agent. So this is a project I have, and just to show, this is the blue. the dotted line is Nickel's native performance, and the blue line is what Jeff and the agent came up with that does the same thing. And this should tell you that I'm pretty good with an agent, but I'm not the Nickel team. Obviously, the Nickel team is 50 to 60 people who do this. That's basically a close to a human millennia of expertise, and I can get within 20% of that sitting in my chair at home with an agent. So that to me is really exciting. Getting within 20% of the best is really promising, because I'm going to do some custom stuff that's not in Nickel, and obviously this is just the way of me benchmarking my own ability to reproduce core operations. Here's a barrier. This is obviously, an interesting thing from a perspective of synchronization and correctness and latency. And so I've implemented, all the standard barriers in NVLink, and AI wrote all this stuff based upon my direction, and then we debugged all the memory coherence model performance quirks, and so I'm getting 5 to 10 microseconds for a 50 plus GPU barrier, which is a good number. So, summary, I think agentic development has come a long way. I was trying it in 24 and 25, and it was hilariously bad in 24, and it was like interesting but not compelling for me in 25. I started really grinding on this in May of 26, and it is a game changer. AI is awesome at stuff we all hate. I don't know anyone in the world who enjoys doing a get rebase conflict resolution. I have AI do that for me now. Like I said, I hate CMake. AI does it for me. I know how to use GDB Valgrind for debugging. I don't enjoy it. AI does that for me now. I do all of my test coverage with GCov in AI as well. I don't submit jobs anymore. I have AI do Slurm direct, or write scripts that drive all of the environment variables and all the testing and performance tool harnesses, even on NVL72 systems. I do say a prayer for all the people who operate public supercomputers who have login nodes. You really need to figure out how to make sure those agents don't go insane and destroy your file system, etc. That's a policy thing. Obviously, we've had dumb users for my whole career and beyond, but AI is a different class of dumb users that we need to administer in HPC. So AI does great at scripts, including diagrams and plots. I know how to use NuPlot, but I have everything running out of Python for Matplotlib now. All the figures just generate, and I obviously check the data. But it, AI is good at Python for obvious reasons. AI will listen to you even when you're wrong. Found that out many, many times, so you have to be very, very careful. AI is brilliant and also pathologically stupid. It deadlocked, and like I said, it did 8 gigabytes of buffering in the eager buffer for no good reason. And so you got to test everything. This is totally unlike a human. You have a talented student, you have a talented postdoc. You can generally trust they won't do idiotic things. You cannot trust AI not to do idiotic things. Everything is trust but verify. If it's not tested, it's probably broken, and it might be really, really broken in a terrible way. Nonetheless, in spite of all of the interesting caveats I've given, my productivity with AI right now for this sort of stuff is about 100 to 1,000x. I have written more code in the past 2 months than I've written in the past 10 years. I'm doing research. I am not doing products. I don't do security sensitive stuff. There's plenty of reasons why you don't want to go all in on AI crazy like this in other environments. But for me, in a research context, it's been fantastic, and I've done stuff I didn't think I'd ever get a chance to do. And even if I put on all the guard bands and get really paranoid and add sort of all sorts of productivity sinks, I still think I'm above 10x, and AI is cheaper than I am. So I think it's a darn good deal. So I'm going to close and just sort of give my analogy for how to think about AI, right? When you build a building, you have an architect, you have an engineer, you have a construction manager, and then you have all the carpenters and technicians that go build the building, right? AI is great at carpentry, okay? It can pound out thousands of lines of code an hour. But it is not great at architecture, and it will not do, engineering safety or any of the or engineering management. You can try to push it to do that, but it's a stretch. So when you think about AI, you're the architect, you're the construction manager, you're the engineer, but AI is going to go out and hammer all those nails. And if you can design the right ideas and set up the right structures, you can build buildings with 3 people instead of 1,000 or something, which is really cool. But if you have all the AI in the world and you don't have architecture, and you don't know what you're doing, you will not get a building any more than 1,000 carpenters with no manager are going to stand up a building you'd feel safe in. So that's the end, and I'll take any questions.
Let's give a thanks to Jeff. Okay, Samir, yeah.
Hi, Jeff. This is Samir. Based on what you have learned with building Vibe MPI, if you had to build Vibe Nickel in the future, are there things that you would do differently?
Yes. So what I learned, I did a lot of top down in Vibe MPI, because the bottom up for me, like I don't know anything about TCP IP sockets programming, and I didn't want to. If I was going to do Vibe Nickel, I would go bottom up, and I would write COM micro benchmarks for NVLink and for IB, and I would build skills, and I would build layers of how do I do this? How do I do a semaphore? How do I do, a message? These sorts of operations, and I would build up those layers, and then figure out how to compose them. And that's of course how smart people actually do this, when they're not trying to do what I did. But that's what I learned, and I learned that the hard way, because when I like I said, when I went on the slingshot machine, it was a disaster because I didn't actually know how the network worked, and neither did AI, and so for 2 days nothing worked. So going and doing real software architecture and building blocks and abstractions and interfaces between things is the right thing to do with AI as well, and it really contains the design space in a way that helps AI.
Okay. So Dan, yes, please. Thank you.
Yeah. Hey, Jeff. This is Dan. Thanks for joining us from Finland. I have a million questions for the next time we're in the same room, and this was a really interesting example, but I'll just stick to 2 that are blatantly unfair. So first one, so you had full MPI implementations in your RAG database for it to learn from. How do you think your experience would differ if you asked your agentic AI to help you build NWChem without showing it NWChem to start with?
Actually, so this talk is too short. I did that, Dan, and that's in the longer version of this talk, which if you want, I could give remotely to TAC and I could share it with you. So I did I really vibe coded a quantum chemistry package from scratch. And it is amazing and also extremely slow. And I can tell you more about later. So and in that case, I can tell you where where I actually had to give up on math as the input and switch to source code, and it was pretty far into a quantum chemistry package before you cannot just go off of the literature of papers and equations and do that. Quantum chemistry is actually a really, really easy thing to do AI on because there's so many papers that explain how to do it, and most of them are good.
All right, we're not going to get into the sentence quantum chemistry is easy, but but I do believe English is a really lousy way to specify software. So my other question though is, you've been an expert programmer for a long time, and what you said is you can be remarkably more productive, and you could pretty easily put out things that were sort of within 20% of what a whole bunch of human experts could do. I know things are changing rapidly in AI code generation, but are we headed for a world, in your opinion, where we're going to have vastly better software, or we're just going to have a lot of software we can produce more cheaply and the whole world's 20% worse?
I think the world is going to be better because, I don't know any context where writing high quality code isn't one of the key bottlenecks for a simulation AI organization, right? I mean, Dan, your users are running quantum chemistry codes that are older than I am and include lines of code that are probably older than you are. And the reason they're running those codes is because it's really bloody hard to rewrite it. And we know what better code looks like in most cases, but it's still knowing the answer isn't the same as having a software instantiation of that answer. And when we can use agents, we can move from bloody hell, I got to go in and type all this stuff out and then verify it to I can whiteboard it, I can define equations, I can describe it, and boom, I can produce the code. And then I can go in and decide if it's any good. I can test it, I can probe it in the same way I would if it was human, but I can crank through that. And now I have the code process 100 times faster than we can with human effort. And we will be able to do a whole lot of experiments that just aren't practical. And I think it'll be amazing. I also think people will produce mounds and mounds of garbage, like just to be clear. But we as scientists have discipline, hopefully, in what we do and the resources that we exploit. And if we're smart, we will empower our grad students to do more research and less typing.
Okay. So I think we may need to, Jeff, this is a very interesting topic. I think we can spend 2 days on this. We are already running behind by 30 minutes. Let's move to the next talk. Let's give first big thanks to Jeff.
Thank you.
Okay. So might be Jeff in future, Mark will try to bring you and